Hello, I'm Kunyu. Recent years, we have been studying control theories and optimizations in microgrid. In order to verify them, we built up a microgrid, a hardware-in-the-loop microgrid to test the performance of our proposals. It is a hardware-in-the-loop microgrid because it contains two parts, the hardware parts and the software parts, which interact with each other in the real time. In the hardware parts, we installed a chemical battery. It connects to the DC bus, passing a controllable breaker. In the meantime, a set of capacitors are linked in parallel to filter the noise in the DC voltage. So, this section can be regarded as a voltage source in the short time scale. And each bridge connected to the voltage source, which is expected to form a voltage source-based inverter. To achieve it, PWM signals from the controllers drives the H bridge cutting the DC voltage to AC voltage. Then, a parameterized ALC filter smooths the AC power before it injects into the AC bus. And so the AC bus can power the load, for example, a water boiler here. To construct a microgrid environment, the software part simulated in FPGA includes more batteries, DC loads, AC loads, solar panels, as shown in the monitor. And in the OpenRT platform, the upper yellow block is the software FPGA simulation. The lower yellow block is hardware input and output. The OpenRT platform can assemble the hardware part and the software part together while exchange their data, their power flows in the real-time scale. And in the console, we can overview the microgrid network. The blue part is the hardware, and the yellow part is the FPGA simulation. Based on the hardware-in-the-loop microgrid, we tested and verified many control methods. Firstly, the fundamental models include phase-locked loops, voltage control, current control, and PWM generators. Secondly, power sharing models such as droop control, master-slave control, and grid forming and following control. Thirdly, regulation models, automatic generation control. Fourthly, economic dispatch models. For example, distributed average integral control here, and microgrid central control. Call for the MATLAB to solve the centralized optimizations. Fifthly, hierarchical control schemes, including the feed-forward scheme and the closed-loop schemes. Here is a demonstration that the distributed cooperative control for the power and energy of battery systems. Running the system and setting the sunlight intensity random change every 5 seconds. We can get the states of the system through the measurements, for example, the voltages. Also, we know the system is stable from the frequency information and the power information. OpenRT simulator can record all the data, so based on the testing data, we can calculate the economic and the stable performance of our control design later. In the near future, we expected to scale up the microgrid and test the control designs in more complex scenarios. We are testing the grid forming inverter the grid following inverter, and a physical MPPT controllers for solar panels. The panel will be installed in the rooftop of our building after the school reopening. If you are interested in our research, the theories, and the applications, you are welcome to check our papers. Also, we have uploaded our program codes for this test bed to the cloud for your reference. Thank you.